Anyway, so this class written for ELC Prague by Mark Basut. He's one of the consultants, part of the ecosystem of Yocto project, our expert in DTOs. He also gave a talk about U-Boot at ELC this week and ran one of the classes for the extended learning things that we've been doing. So I knew nothing about DTO relays. He couldn't be here today because he had to leave early. So I spent a lot of time with him, learned all about it. So this could be interesting. So we'll take it forward. And this presentation worked 7 times before I gave it, so this should be interesting. So who knows about device trees? Okay, who knows about device tree overlays? Who doesn't know about device tree overlays? Okay, this will be interesting. So, something new for some people. Those of you who know it, you can certainly help pipe in if I miss a point. But let me just give the presentation. Data structures describing hardware is what the device trees are. Usually passed to the OS to provide information about its structure and its topology, made up of nodes and properties. And nodes can contain other nodes and properties to describe the hardware. So it can discover the hardware for you and share it with the Linux kernel. It can also, their properties are name value pairs, quite simple. And we give a link to where the description is for a device tree in Wikipedia. And it can create cycles by means of, let me add the microphone. Okay, let me get that so we can capture the thing. So, this is for a big one. So, okay, yeah, plug this in. If it wants to. Here we go. So, yes, device trees. These are predefined device trees passed to the kernel, so the kernel can find where all the hardware is for that particular board. So it does not have to do self-discovery. That may not be able to find the devices that are there. So we're describing how the trees made of nodes and properties, and we have each property is a name value pair, and we give you links to where to find out more information on Wikipedia. So, and DTs can hold cycles of P handles. So I have no idea what P handles were. P handles are ways to describe a block of device tree stuff that you can then use as a reference in other parts. And it creates a cycle in the tree. It points to either the same part in the tree above it or some part of the tree at a different tree, so that you can have shared definitions across different device types, so that you can really link together, for example, your cache definition with your device definition, with your bus definition, or the combinations of those. So that's really a nice way to carry forward stuff between the trees, make references that are consistent. And so here's an example of a DTS device tree. In this example, we have gave it a name, and we always include something. There's a processing that works like C, where there's a header file that can bring in predefines that define the general class of this device or board. And this example is the RealView, ARM RealView EV TSI, and so we're going to describe how we extend that model with this one. And here we're going to have, by default, all the address cells are 1 and the size of cells are 0. So we just commented out because that's the reference, but we keep the reference there so people can remember. We define the enable method, and then we define a CPU. And CPU in this case is the instance is 0. They'll match up with the registration number, the reg number, which is 0. So the device type of this is a CPU. And we then do the compatible. Compatible is how you describe how to find this device, match it up with the content, so the device loader can find it. So in this case, it's always the architecture, the vendor rather, which is ARM, and then the device type, which is in this case RealView-SMP. Then we describe the actual CPU, and what we're adding here is the next level cache. And here you see a P handle, which is the ampersand, and the definition L2. The L2 is inherited from the include class at the top, so you can really layer this information, inherit stuff cleanly. And at the bottom, you also define the PNU and add 4 interrupt affinities. In this case, you see the P handles for these objects, the A90, A91, A92, A93. So you have your interrupt class set up for your PNU. So, the problem that we're trying to solve. DT started on small devices, size of a little refrigerator. Then it was also mostly static, which was enough for the day. And everything was fine. You see, bake it into the ROM, so that was right there available. and obviously modified by the bootloader. It had to do some real time little update before it passed it on to the kernel. That was fine, and went to first on PPC, went to ARM, and there was always slightly variable hardware, and we had which you could solve by patching the DT in the bootloader, as I mentioned earlier, and solve by multiple DTs, solve by incorporation between the boards and the DT files, but this does not scale. This is fragile, especially in the world we come to many daughter boards under many names, hats, lures, capes, whatever. Also, the explosion of FPGAs, systems on chips, and the combinations and variations on those themes. And so that combination hardware became just very difficult to maintain with static DTs or even modified DTs. So that's why they came up with the world of DT overlays, where you can dynamically update the device tree and trigger the kernel to recognize these new devices as they come online, as they're attached, as they're discovered by some methods. So, DT overlays. And it describes hardware, as do regular DTOs, and it describes the changes you like to do on a particular feature set or board, expansion board, daughter board. And in this example that we're going to be using for the class today, this is a very simple, the simplest DTO. And it's going to present that in this case, again, the address cells are 0, size are 1, and the cell sizes are 0. Required keyword, fragment, that's what we're going to be adding in a fragment. And within that fragment, we're going to be adding an overlay. In this case, again, address cells 1, size cells 0, and we came up with the name hello. Very, very clever. And it's instance 0, which we mapped in the reg down below. So we're adding one thing, and this is the instance 0 of that object. And we're going to give it a compatible so it can be found when you're going to be installing this. And also match up with you always have an accompanying kernel module that matches up with it. So you want to ensure that everything's compatible and they match up. In this case, we gave it the compatible hello, very clever again. And we gave it the word as the vendor and the device type is DTO. That's just, he just made that up. It doesn't have to be DTO. It's not magic. I thought for a while it was, but no. He just gave it the name DTO just for the sake of the class. And that's it. That is a minimal. I'll just mention also target path. This is where we're going to introduce this overlay into the device tree. In this case, we're going to add it to roots. But we could put it anywhere inside the tree that we know is there. So let's go on. So here's a more advanced example. This is a board that Mark had in his one of his consulting assignments. In this case, the board has a USB, but by default it's disabled. It also has an Ethernet port, which again, by default is disabled. So what this DTO overlay does is turn those two on. And so you see an example, fragment, of course, required keyword. The target path, in this case, is system on a chip, SoC, and this USB and the instance number that was assigned to it in the inherited file, which is not included in this example, but it's up there somewhere. And in this case, status, okay, that is in that vernacular, enables this device. So when this kernel, this DTO overlay installs, it will enable the USB. In the second fragment, perhaps fragment 3, again matches up with the reg, number 3. Target path is SoC Ethernet with also an instance number, in this case, FF7 and a bunch of zeros. And then the required section overlay, again, status, okay, we just turn it on. Very simple. In this case, we also describe how we're going to physically connect the data stream to it. In this case, it's a gigabyte modules, II something. This is some standard that is brought in. And that's the physical mode of connection, which enables just a gigabit fiber connection to the bus inside the SoC chip system. So this is a more, very simple, more advanced, but again, very simple DTO overlay. Going on. So we're going to be doing some hands-on exercises. This will be fun. And we're going to, Mark has prepared a simple layer that will provide the family of things you need, the minimal family, to enable a DTO. And in this is going to be the kernel patch to enable the config of S to bring in dynamic DTO overlays. And we're also going to have a demo module that is matched with it. We have the DTO source, which we can take a look at. That is the source of the DTO. And we're going to compile it on the target, and we're going to load it. To give you an idea what the layer is, this is again a pretty minimal layer. This is about the smallest you can do. And let's describe what is here. First of all, this is a Yocto project compatible layer. So we have layer.conf. Nothing special, just enables the objects within this layer. The PDB append, all that does is add these packages to the image. In this case, that's in the DTC, that's the device tree compiler. And then the module, and then the DTO. So 3 things we're going to add to the image. He gave us a minimal image, the smallest possible image, just to get this out of the door. So that's under images, and that's what's, oh yeah, okay, that's that. So it's a minimal image, nothing else. We just wanted to boot, be able to compile our things and run. And we'll see the layer of that. It just inherits the base image type. The next thing is the DB append for the DTO file. DTO file, whoops, there. Okay, so in this case, we're going to just copy over the raw text file to the target. We're not going to do any processing with the as it gets loaded. We just want to install it. So the simplest thing, install this thing in the destination directory lib firmware /DTO. So we just want to get that raw text file into the target, into a known place that the compiler can find it. Next thing is the module. You always have to pair up a module with the overlay. In this case, the overlay is going to print debug messages when you write a file into this special location. Config.fs, everyone know config.fs? So config.fs is a special directory structure that waits for events like creating a directory or something. When that happens, it triggers configuration events with the other kernel stuff. And when you delete that directory, it's been hooked up, and it will then remove content, triggers and remove. So that's what we'll be doing, setting up what this is doing. And so also we need to do 2 more things of magic. One is to enable the patch to enable overlay FS to know about DTOs. Now DTO overlay is not part of the kernel. It's not part of mainline. You cannot turn it on. The reason is because the kernel maintainers felt that this technology could really open up your device to malicious things. They thought this would make it unsafe. So as useful it is to developers, they're nervous about it. So if you're going to put it in, they want you to put it in knowledgeably and then hopefully remove it before you deploy your target. Or if you're going to put in your target, make sure it's locked down and guarded. So in that case, whenever you do a DTO, you always have to bring in the components of the kernel to enable the overlay support. In this case, it's a patch to the kernel to enable recognizing DTC flags, a patch to extend the config.fs to be able to understand when the dynamic device tree overlay comes into the system, and then a config flag to turn that on. Turn on config.fs, turn on the overlay support. So let's take a look at the kernel module. Let me just actually jump over here. This is the kernel module, simplest possible kernel module. When it's loaded, it's going to say hello somewhere. Oh, it's just right inside. So when you probe it, it will then give this message to say, this is my line I got installed in the function line. When you remove it, it gives, again, this function line that came in. So you can see where it actually executed this code. And it also sets its compatibility so they can know how it's related to the overlay itself. Because again, so you have to combine, make sure this matches up inside the kernel module, matches up with the device tree entry so that they will be brought in together. And then just simple registration of the driver for it. So that's it. That's a very simple kernel module in the minimalist. So let's go back to the presentation. Okay, hands-on. So what I've done for you is I've made the project. I've appended the necessary content to the project, which is the layer, is added to the BB layers. I've reset the machine to QEMU ARM, and I've built the project for you. So the next thing to do, I've also done a clean. We also built the core image DTO Macro demo. So I built the image for you, the minimal image to do this demo, and we're going to then run it. So let's go ahead and do the first step. It didn't quite show. So everyone in your class, let's switch over to /scratch Pokey. And to do a clean shell, I recommend you do a bash. And we're then going to source OE, and then build -DTO. We're going to go into the pre-built project for the DTO example. And I forgot to add that line to the slides. I'll add that line to the slides. Okay, is everyone in their build DTO directory? Who's not there? Okay, we'll just wait a second. So I'll give you the history. Can't read it? It's in the slides. Oh, I'm sorry, that part is not in the slides. Let me make this bigger then. No problem. Okay, let's go to... I'll have to restart this session, give you a bigger... Oh no, I can drag it more. No problem. Let me drag this. Come on. How's that? Let's do history. Tail. Oh, it just shows that. Yeah. Okay, is everyone in the build DTO directory? Who's not? Okay, let's go on. So we're next going to do the run QEMU no graphic. Oh, it won't let me do that. No problem. I hate typing, so I'm just going to cut paste. Oh, we'll have to log in. My test account did not have a password. Okay. Right. Excellent. Switch back here. Okay, when you're there, go and log in, root, and then we, of course, disable the password. So is everyone in their QEMU instance? Who's not?
No, I'm getting errors.
You're getting errors.
Mine required I actually log through.
Sorry?
Mine said had to run through. I understand why it has that. Keep before 5.
You have a very special instance.
Did you shut down your machine for the last exercise?
Yeah. It's on the 4th. That's all after you do other steps. The source then. It's missing the slide.
Yeah, if you didn't shut down the QEMU from the previous exercise, then you probably have one running in the background, and that will block you getting back into QEMU. So for those of you ready to go on, we'll wait, but I'll just mention the next step on the next slide is you're going to compile the DTO source, that's DTS, and you're going to compile that on the target. And it'll be pretty instant. Are you back up?
It's coming up.
Okay, cool. We'll just wait for a second. what's going to be happening is we're going to compile the source code for the device tree overlay. We're going to then copy the output into the config sys for DTO that we created when we patched the kernel. That will trigger the event of loading that device tree fragment into the device tree, and it'll also trigger the loading of the kernel module that's associated with that for the compatibility strings. And then once that happens, you'll see the messages from the kernel module saying that it got started. And then we're going to probe around and see that it is in fact there in the tree in a couple ways. And then we're going to unload it. You'll see again the event from the kernel module telling you that it did in fact execute the removal code.
Yep.
So you up with us? Okay, so I've compiled my overlay, and now we're going to do some magic. We're going to copy that output from a magic location, put it into temp, into the special config fs subdirectory DTO. Oh, I'm sorry, we have to make the directory that's parent to it. So you can't skip ahead on this one. You have to follow every step. Okay, I'm going to create the parent directory, and then I'm going to copy the compiled overlay into that special directory under config.fs. And you see you got a message from the probe in the kernel module. Okay, yes?
I have my terminal, but I can't type in it.
Okay.
That was it.
Terminal is transaction to.
The QMU?
Oh.
You can still
Yeah,
SSH into the IP though.
That's weird.
I had that a couple times. I just killed the QMU and restarted it, and it worked.
Get a special touch. So the advice was if you get a QEMU terminal but you cannot get it in the output, just kill the QEMU instance and try again. Killing QEMU, of course, is Control A and then the letter X. So the DTC? Yes. But it's still running on the host. You'll need to. So the worst comes to worst thing is you get that account. Oh, okay. I'm trying everything now. Yes. Try to compile your code. Okay, we solved one problem. Who else is blocked? No one. Excellent. So you saw, and you can see in my example, that it actually found the kernel, the DTO, loaded it, triggered the kernel module, and you see that there's a message from the probe that installed it. So you've made the round trip. Now let's play a little bit. Let's just confirm that it's there. And this is part of your debugging bag of tricks to know that in fact what you thought happened actually did. Let us see that it's inside the proc tree for DTs. And there it is. Hello, instance 0. Woohoo. So that's one trick to confirm that in fact it did load. Let me show you the second trick I got from Mark about ensuring that it's in fact there, is that when it actually, the overlay patch will give you some information. When you, in that special directory that was empty, when you loaded the kernel module, triggered this event, it creates a couple things. One a path file and one is a status file. So if you cat the status file, and it will not do, oh, of course, /status. It doesn't give me. If you cat that, it'll tell you it applied. That's how you can confirm that, in fact, the system applied your overlay. And let's just see what's inside the path file. I'm curious. Nothing. Okay. Just solid root of the device tree. Okay, everyone see that their kernel module is, their overlay is definitely installed? Okay, let's go on and take it back out just to complete the life cycle here. Okay, I removed that special directory, the code behind it, saw that, triggered the event in the kernel module, and you see that there's remove code and DTO remove. Magic. Okay, did everyone get it removed and see that special message? Your hi mom message? Okay, we'll wait a second for everyone to catch up. Okay, is everyone with me? Cool, the demo that worked. My goodness. Okay, let's continue on to the slides. Okay, so let's just go on to the encore of this presentation. Let me get rid of the thing anymore. So, by the way, let's go ahead and kill the instance. Let's clean up our thing for the next presenter. Control AX will kill your QEMU instance. And you did a bash shell to begin with, so I'm going to do an exit to get back a clean shell. And let's just make sure it's clean shell. Yep, nice and clean. Okay, so everything is clean and everything. So let's go back to our presentation and make this book. Were there any questions, by the way, before we go on? Okay, we have one person being helped in the back, but cool.
I think we'll work through it. I followed along pretty well.
Clever touch. Very good. Okay, so let's just do a couple more topics about the DTOs. This is an example of an FPGA Manager. In this example, this is actually adding microcode into your ASIC, FPGA. So, in this example, is a fragment, again, required word. And inside of the fragment, there's a path that's really installed into the FPGA Manager code and an instance that came inherited from some inheritance above this file. Region 0. Region is the new keyword. It used to be area, but now it's region. We changed it in the last release of DTO. And compatible, you have to match it to compatible to make sure things work. Ranges, that's just some magic about how this is going to be installed and as a microcode. And then the magic stuff. This is the file to the firmware. It's going to be installed into the FPGA. And the compatible, make sure it matches up. Version 0, there's 0. In this case, it gives 3 objects, and that's how it's measured up here. So, and the range is there. So, this is how you would install microcode into your FPGA. So, a little bit fancier stuff, but it's very dynamic. Let's go on. So, interesting stuff. Why, again, is the config overlay code not part of the mainline kernel? Again, it's for security. If you're going to do this, you really should know what you're doing and lock it down and don't block the ability for any outside influence to get your device tree, because at best it'll break your device, at worst it'll do malicious stuff to your device. Example, U-boot. A lot of people do that. U-boot now has support for DTOs to bring in stuff. It's a way to really enable developers the stuff, so you can bring in. And one example is for each board variation, have a DT table burnt into the code, but have a DTO registered with U-boot for the actual board that you're releasing. So you can, that way you can kind of do the best of both worlds. DT locked in, DTO to match it to the actual that release. Example for newbies, if I was going to do DTO device trees, this is what I would do, and you may want to do it too. Is you start with the DTO first, try to get it to load, as the example above in the demo. Then take a working DTO overlay, put that into the U-boot, and then start debugging your kernel module, to get the kernel module working. And once all that is working, then you know that you can then, with confidence, move your DTO code into your DT. And that's a way to just step through the steps nice and safe and really easy to debug. Going on. Recommended ways to load a DTO. I asked them, what is the recommended way to load a DTO automatically for you if you want to get into more automatic? He said, no standard. So he said standard ways, of course, people might do it. Well, the usual ways, I guess is a better word. Sysdinit or systemd. I've seen examples for that. They're on the line a lot of examples you can pick up. Custom scripts, people just script it. And again, as you mentioned, U-boot now supports DTOs. That's another technique. Debugging techniques, I've shown you a couple for live. The proc device-tree, that's how you saw that was loaded. Configure test interface, again, I showed that to you, and Magic creates that status file that it got installed, and that's how you can just double check. Common user errors. What's going to break most often? Spelling is going to break most often. And part of the thing is that, there's just warning, the DTC, the compiler, really has weak verification. It will compile it, it won't verify. So you can put crap into it and it'll just give it right back to you and not tell you that you have problems. So that's what you have to watch out for. Anything special about DTOs? You got the project? No. And that's great. Nothing special. We just make sure it works. I'll just mention it's part of the open embedded core layer, so it's provided to everybody. So that's why it was easy for me to just add that into the image at the top. So that's where you can find it. Examples in real world, Raspberry Pi for their hats. BeagleBone, their cape manager, uses DTOs to enable their, what they call capes. And some Intel boards also do DTOs. DTs are not a standard for Intel boards, but some do it, and you can in fact have a CPI work with DTOs for boards. And this is a kind of way to get best of both worlds. And ACPI, of course, is their power management and their device management mechanism for Intel boards. Because DTs are just so useful. More about DTs, again, the org path. Also, here's the specification for the language. You can path to that. Contacts, Mark, he's a great guy. He knows all about this stuff. He's happy to answer questions if you want to hire him. He's a consultant, part of our ecosystem, great guy. And finally, he gave a speech about U-boot, a talk at ELC just a couple days ago. And you can find references to DTOs in U-boot and also learn more about U-boot from there. And contact. Okay, that is a presentation on DTOs. Any questions?
We also covered DTOs in the EAL class, so there's some materials online for EAL as well.
Okay, so the comment was EAL classes also contains content for the DTOs. Thank you, Tim. So we're getting that information out there. Okay, more questions? Cool. Okay, let's take a break, and then we'll start with device dev tool. Okay, thank you.